So in this video, we're going to show several ways of computing this integral, and we'll take an in-depth view on it. So, of course, let's start from maybe a special case. So we want to evaluate this. But let's start from a special case which is particularly easy. Suppose that this n is odd, and the odd case turns out to be much easier than the even case, but we'll see when and how. So suppose that we were given the integral of this form, then what we can do to proceed is we can write this in the following way. So this is the sine of squared here of x to the power of n, that's power of 2n times the sine of x dx. And then we can write this integral as, so sine squared is 1 minus cosine squared, of course, of x, all this to the power of n, and of course times the sine of x. And the reason for doing this is that this sine is almost the derivative of the cosine. So if we make the substitution t equals to the cosine of x, then of course dt becomes minus the sine of x dx, and then this integral becomes, so this is the integral, and here we have the minus sign, and we can actually flip the order of terms here, and then we'll have minus 1. And taking into account this minus with the minus dt, okay, you know what, maybe we'll write this in the following way. So it's going to be minus 1 to the power of n t squared minus 1. It's just flipping the order here. And then we have also, you know, this is minus dt. So minus dt here. So and then all of this to the power of n, of course. So it becomes this integral of minus 1 to the power of n plus 1. And here it's the integral of t squared minus 1 to the power of n dt. And of course, this integral looks very easy because it's a polynomial, but if we really want to evaluate, we can use the binomial formula. So if we want to proceed, we may proceed in the following way. So we'll write this. This is just the sum as k runs from 0 to n. And here we'll have n choose k. And here we have t squared to the power of k. So it's going to be to the power of 2k here. And then times, here we're going to have minus 1 to the power of n minus k. This is from here, and this is dt. And of course, we have minus 1 to the power of n from here, right? Minus 1 to the power of n plus 1 from here. So now if we were to proceed and use the linearity of the integral, so actually this can be taken out, at least this minus 1 to the power of n. And here we'll have minus 1 to the power of 2n. Forget this one for a moment. And minus 1 to the power of 2n is always 1. So we can write it in the following way. So this is going to be the sum of k runs from 0 to n. Okay, so with this, what we will have, minus 1 to the power of minus k is actually the same as minus 1 to the power of k. So all in all, the minus 1's become minus 1 to the power of k plus 1. Okay, and here when we're going to integrate t to the power of 2k, it's going to be 1 over 2k plus 1, the binomial coefficient here n over k, so n choose k, we have it here, and then t to the power of 2k plus 1, and of course not to forget plus a constant. So if we want to plug it in back, so we can have this nice formula. So the integral of the sine of 2n plus 1 of x dx can be evaluated in the following way. So this is just the sum as k goes from 0 to n. It's minus 1 to the power of k plus 1. Here it's going to be divided by 2k plus 1 and choose k. And here, of course, we're going to have the cosine of 2k to the power of k plus 1 x plus a constant, and that's the answer, at least for this case, of an odd power. So that's an interesting formula. But of course, the standard approach is here. This is a special case for an odd n, and there is actually an approach that works for every n. So let us now see this approach with the recursive formula here. So the other approach says the following thing. So we want to compute, regardless of whether n is even or odd, we want to compute this integral. Okay, and we'll denote this by in, and we'll relate in to in with a lower n. And we'll see that the jumps here is going to be by even steps. So let's write this integral. So integration by parts does the job. So let us write this as sine of x to the power of n minus 1 times the sine of x dx. okay? And integrating by parts, we'll choose this as u. So in the next step, we will differentiate this, and this is going to be v prime. And so, of course, it's going to be uv. So v, of course, is the integral of sine. It's intermediate, it's minus cosine of x, and then times u. So it's the sine of n to the power of minus 1 times x. This is it. And now it's going to be minus the integral and of v times u. But v is minus the cosine. It already contains the minus. So let's just change this to plus and write cosine of x here. And now we need to differentiate sine to the power of n minus 1. So it's going to be times n minus 1 sine to the power of n minus 2 of x. And then we have the internal derivative. So we need to multiply this by the derivative of the sine, which is again a cosine. So we will write cosine square and all of this dx. And now if we rearrange this, so we will write this in the following way. So this is minus cosine of x. And here this is sine to the power of n minus 1 x. And here we're going to have n minus 1. And basically, this cosine squared, I'll already say that I'll write it as 1 minus the sine squared of x. So we will write it in the following way. So here we'll have sine to the power of n minus 2 of x. This is times this 1. And minus the sine to the power of n of x, all of it dx, of course. We've got rid of the cosine. And this is the integral. So, of course, if we separate it now, if we plug it in, then we get the recursive formula. So in is minus cosine of x times sine to the power of n minus 1 of x. And here we're going to have plus, and here we're going to have n minus 1 times this integral, which is n minus 2. And minus, this is again n minus 1 times in. And therefore we can, switch this to the other side, and here we have 1, and this is going to go with plus, so it's going to be n minus 1 plus 1. So we're going to have n times in minus the cosine of x sine to the power of n minus 1 of x plus n minus 1 in minus 2. And the final step would be to divide by n. So we have this recursive formula that it is minus 1 over n cosine of x. And here we're going to have sine n minus 1 of x. And plus here, if we divide by n, 1 minus 1 over n. And this is in minus 2. That's the formula that is typically derived. And of course, it's perfectly valid and great, because essentially allows us to relate in to that of a smaller power. So n is at least 2, because of course for n that is equal to 1 or 0, we know how to solve the integral. And so if we start from an odd n, then by skips of 2 we'll end up at n equals 1. So it's the integral of sine that we can compute. And for n even, we'll end up with sine to the power of 0, which is basically the constant 1. And then we'll have the x term added in the integral, and that's the common formula. But I said that I want to make this in-depth review. Sorry for staring at the board all the time. And let me give you something else here. And so this is, what we've been so far is a perfectly valid solution, and it solves the problem from end to end. But if you want to take a more in-depth look into that, so there's actually another way of looking at it. So actually, anyone who played with trigonometric identities knows that cosine of n theta can be written actually as a polynomial in theta. And in fact, there's a name for those polynomials. Those are the Chebyshev polynomials. So we can write this as cosine n theta as a polynomial, as powers of the cosine theta. And something similar happens. This is called the Chebyshev polynomial. I will not go deep into this here. It deserves a separate video, but there is another associated like Chebyshev polynomial such that this identity holds, and basically recursive formulas can be derived for those for Tn and Un that enables to compute those polynomials to every degree. So that's a way of going from a function of theta to n theta by taking the powers. But what is the other way around? Can we write a power, for example, sine to the power of n as this combination of harmonies of sine as this. We would like to write this as so maybe a k sine kx n plus the k cosine kx. And it turns out that this is possible because, you know, we can, from even this expression, we write this as this linear term as this polynomial, and then with all those degrees, it seems reasonable that we can arrange it this. And in fact, so here actually k goes from 0 to n. So this is a finite sum, and it can be done. But in general, for every function, not just this function, this is called the Fourier series. In this case, they terminate only at n, but if we take the infinite sum, we can approximate any function. So this is kind of gives you, you know, as a motivation to Fourier series, or maybe not motivation, but, you know, a simple way of seeing it. So here it terminates at n here. And so the interesting thing here, of course, is that we can actually show that when n is even, then sine to the power of n is an even function. So we're going to have this, you know, series of only the cosines of the even functions. And if n is odd, we're going to have only the sum of the sines. So indeed, it is possible to find this expression, and it terminates at n. So if you wish to do it, there is a nice way to compute it. So there's a way of computing those coefficients in terms of integrals and using orthogonality, but I would like to look at the Euler's identity for this purpose. You know, you can stop watching now if you got your answer, but if you're curious to see how another way of looking at it and deriving the other formula, then, you know, sine of x is this is the Euler's identity that deserves us, of course, a separate video, because, you know, it's a wonderful identity. And then the sine to the power of n is this to the power of n, and so we can write this as 1 over 2 to the power of n. And here actually 1 minus I, 1 over I is actually minus I. So we can write this maybe as minus I to the power of n, or minus 1 to the power of n times I to the power of n. This is what we have here. And then for this sum, we actually for this you know, for this expression, we use the binomial formula. So this is going to be n choose k. And here we're going to have the following. So k, of course, runs from 0 to n. And what we're going to have here is e to the I kx and times e to the minus I n minus k x. That's the sum that we basically need to evaluate. And once we evaluate this is actually will turn out to be, so the real part, of course, this function is real. So the real part is, you know, when we decompose this, is going to be either the sine or the cosine, but we'll see how it works. And then, you know, integrating this is basically integrating a linear expression, so we'll derive this nice identity. So if this looks interesting to you, just keep watching. Okay, so let's proceed. So now if we continue with this sum, so let me write it here, and we'll get back to the original formula. So here we have minus 1 to the power of n, and here over 2 to the power of n. Oh, I'm sorry, I forgot. I need to have here minus 1 to the power of n minus k, of course, right? Because of this minus. So I took this e to the power of n minus k, but forgot about the minus. So, of course, we have this minus here. And now the beautiful thing about this is that you can take this minus 1 to the power of n outside to meet this one, and they will always be 1. So we can actually, you know, forget about this term. Let us write it this way. So this actually equals. So we're going to have I to the n here over 2 to the power of n. And here we're going to have the sum. Here we're going to have n choose k, as k runs from 0 to n. And what we have here is, here we're going to have minus 1 to the power of minus k. So it's minus 1 to the power of k. And here we're going to have e to the power. So if we write it with the minus, so it's minus I times n minus 2kx. Hopefully I didn't make a mistake, and indeed if we open the bracket, so it's going to be minus I n x and plus, so minus minus plus 2kx. And so we have this formula, and now, you know, for convenience, actually I is e to the I pi half. If you don't know this, well then, you know, It's a basic fact. And now we can actually use this to write. So we finally arrive at the following identity. So sine to the power of n. By the way, something completely analogous can be derived for the cosine. So I'll leave it as an exercise. And so here we're going to have this sum as k runs from 0 to n. And here we're going to have minus 1 to the power of k over 2 to the power of n. And here we're going to have n choose k. This is it. Hope I'm not forgetting anything. Yeah. And here we're going to have minus I n minus 2k x. And you know what, let us write it this way. So it's going to be minus I, so we need to add, so I to the power of n is of course this. So with this minus, so we actually need for this to be a plus, it's minus pi over 2n, right? And so what we get here, then this is you know, due to Euler's identity, this can be written as the cosine of n minus 2k x minus pi half n, and here it is actually minus I, the sine of this same thing, minus 2k x minus pi half n. And now when we equate the real and the imaginary parts, so the imaginary part here is 0, so what we get is that for every n, the sine of an x is the sum, k goes from 0 to n, and this is minus 1 to the power of k over 2 to the power of n. Here we're going to have n choose k, and here it's going to be the cosine of, you know, n minus 2k x minus pi half n. This is it. This is the identity, and so we'll see, you know, for n even and odd, how does this turn to a sine series or a cosine series. And another identity that we from here that we get for free is that actually we've proved, you know, just along the way by computing, that k goes from 0 to n here. So if we take minus 1 to the power of k divided by 2 to the power of n and choose k, and here this is just the sine of the same thing, so it's going to be n minus 2k times x minus pi half n. This is for every x. This is just a 0 function. So that's a non-trivial result. That interesting. So we have this, right? So now if we wish to integrate, then integrating this is an easy task. So because, you know, we need to maybe let me write this integral that for every n we have expressed this. So the integral of the sine of n dx becomes this sum. Of course, we'll need not to forget the constant, as k runs from 0 to n, and here we have minus 1 to the power of k, 2 to the power of n, and here it is just going to be, so we integrate the cosine, so this is just the sine of n minus 2k times x minus pi half n divided by the internal derivative here, which is just this n minus 2k. Okay, and now when I'm teaching my students, is I always teach them, oh, n choose k, of course, is to look where the formula might fail. And so let us take a look what happens then, you know, failing is division by 0. So what happens if this turns out to be 0? So the only way this can be 0 if n is even. So because if n is odd, then n is not equal to 2k. So suppose that, you know, n is even, but then if n is even, then this this term, so we'll have something like sine of alpha minus an integer multiple of pi. So it's, depending on k, it's just plus up to sine, it's going to be sine of alpha. And so imagining that this term is not present when n tends to 2k, so this is 0, but the sine is also going to be 0, so the limit exists. So the limit actually is going to be x by the famous limit. So, and of course we need not to forget the constant here. So that was an in-depth look and to evaluating this integral, and along the way we've got an added value, namely that we've expanded this sign into this Fourier series. Now what we need to notice here is that for n that is even, right, so that is actually going to be, for n that is even here, so we have this pi. So if we open this with the trigonometric formulas for the identity for the sum, so for n is even, this is actually going to be a sum of the cosines, and for add is on, this is going to be sum, odd is going to be a series of sines. So in a way, we have computed the Fourier series of the sine to the power of n, and computed like n various integrals here. But maybe this is a subject for another video, because it's getting too long, and I'm really happy if you watched up until this point. I really hope that you enjoyed this video, so please consider sharing and subscribing to my channel so that I will be motivated to produce more quality content. Thank you for watching, and I really want to thank all my subscribers. All the best, bye for now.